out. You can find some of them online, or maybe you have access through your university to them. I just want to give you a sort of brief outline of what we're going to discuss. So we're going to start with amenability. And this is a way to introduce many of the topics that come naturally through the study of actions on Hilbert spaces. Then we're going to introduce property T, which I will abbreviate just with this T, and relative property T. And this is roughly a breakdown by day, but we'll see how it goes. And then 3, we're going to do the Haagerup property. And what is called the GNS construction. And during Pierre's introductory talk, he discussed these two notions of property T corresponding to affine isometric actions versus just isometric actions on a Hilbert space. And this GNS construction is going to tie these two things together for us. And then, oops, I skipped 1, so this is 4. And 3 is going to be property T / relative property T for SL and Z, and that's the property T, and then relative property T is for group pairs, so it will be SL and Z semi-direct product Zn. Maybe I'm going to write an n-1 here. And this is for n at least 3. So we're going to more or less give a proof of that. And you're also going to see a different proof, I believe, for the real case during one of the discussion sessions by one of the participants. And then finally, on day 5, we're going to look at another equivalent formulation in terms of median spaces. And characterizations. And that could be like its own week. So we're going to more or less focus on the simplicial case, finite dimensional, which is basically cat0 cube complexes. Okay, so that's an outline for the week. We'll see how things go. Okay. So, amenability. Okay, references. So, also, all of the world that you can study with these properties basically is for locally compact second countable groups. Okay, and an example of that would be gamma, a discrete countable group. And locally compact second countable essentially tells you that your group G is going to be locally compact, obviously, and it will be an increasing union of compact sets. Compact. Okay, and the reason you want to look at that essentially is because it gives you harm measure. So locally compact means that you have a well-defined notion of how to measure things in your group, which is left invariant. So a lot of things, a lot of technicalities that come in when you're considering the locally compact case can be avoided by looking at the discrete case. So that's what we're really going to focus on. And if you understand the discrete case, you can understand the more general locally compact case by understanding a little bit of measure theory and the discrete case. So I'm mostly going to be defining things for discrete groups. Sometimes I'm just going to casually go to a locally compact group and kind of assume that you know what that means, but you can always think about discrete groups. Okay. So with that in mind, we can define the following. So again, gamma is always going to be a discrete countable group. Notice I use G for this. I'm going to really make that distinction. If I write G, I'm going to be thinking of a honest locally compact group as opposed to this discrete countable group. P is between 1 and infinity. We will define LP. Let's write it this way. LP of gamma is the set of functions from gamma to C that are P summable. This board moves a lot. P is finite, okay? And that's for P finite. And then for P equals infinity, we have L infinity of gamma is the set of functions that are bounded. So the sup over x and gamma is bounded. Okay, so these are going to be spaces of interest. And of course, these are metric spaces. So we have, this is the p norm of f raised to the pth power. And then so we have a metric associated to that given by the pth power of f minus g p norm. Okay? Okay. Oh. I guess like this. I'm taking the pth root because I put a p there. I didn't want you to get confused between the two p's. Okay? Okay. Right. So I have some exercises that I'm going to distribute. For example, maybe I'll go ahead and define the action. So gamma acts on LP of x, gamma. By looking at gamma f applied to x. Well, gamma f is supposed to be a new function, so I need to tell you what its values are at x, and that is after moving x by gamma inverse. So, yes? Okay, thank you. Is this, can you see what I wrote? No. Okay. Thank you. So yeah, so if you can't see what I'm writing, you should tell me. I think it's just a height thing, right? Oh, but you're complaining about the light? Okay, you want me to turn it off, or? I'll like laser. Is that better?
Oh, thank you.
But now everybody's gonna fall asleep. No sleeping. Okay, so gamma f, but this is okay, right?
That's okay.
Okay, and I guess was that true for everybody as well? Okay, so speak up. If you don't understand, this is your summer school. Ask questions, complain. Okay, so gamma f applied to x is f of gamma inverse x, okay? And I leave it up to you as an exercise to prove that this is actually an action. Okay, there's this inverse here. Why is that inverse there? So it's an action. It preserves the norm, and therefore it's an isometric action. Okay? Then there's another exercise that I won't describe now. But I really want you to do those first three exercises. And even if you are like, yeah, I saw that before, really make sure that you got that down. Because if you don't, some other things will be a little more complicated. Okay. Questions so far? Okay, so amenability is kind of special in that if you look at Wikipedia, it will give you like 14 equivalent definitions, and that's not even all of them, okay? So I'm going to give you 6, okay? And one of the exercises, which I encourage you to think about, is to play around with which directions you can prove. I'm not really sure if off the top of my head I could prove the equivalence of all these 6, okay? So definition. So gamma is amenable if and only if one of the following equivalent conditions hold, okay? So the first thing you're going to do is complain that I'm putting an if and only if and the following conditions are equivalent in a definition. So this is a definition / a theorem, okay? And your, one of the exercises is to basically go from picking one as your definition to proving the equivalence of all of them. And if you can do that, I would be very happy, and you can show me so you can remind me how to do it. Okay, so I guess I'm not supposed to write below this line. Is that right? Yeah, okay. So 6 conditions. I'm going to put 3 here and 3 there, I guess. Okay, so 1, there is a, so I'm going to put the conditions down, and then I'm going to put some definitions down, okay? So there is a left invariant finitely additive measure on the power set of gamma. Okay, so 2 to the gamma is the power set. 2. Okay, can I have like epsilon more for 3 down here? 3. So 2, there exists a sequence of Fulner sets. And 3, L2 of gamma, kind of squiggly, less than, greater than or equal to I sub gamma. What does that mean? Means L2 of gamma almost, has almost invariant vectors. And I'm going to define what almost invariant vectors are, I guess, on the 3rd board. And that's it for that board. And I also forgot to say over here that for L equals 2, or P equals 2, this is called the left regular representation of gamma. Okay, so gamma acting on itself by left translation, looking at the corresponding Hilbert space, gives you what's called the left regular representation. And actually, how long is my talk? Okay. So did we start at 10:15? Okay, so I have 1 more hour. Okay. So 1, 2, 3, 4, 5, 6. So 4, what's 4? K compact metrizable. And you have gamma acting by homeomorphisms on K. Then there exists mu, a probability measure on K, which is gamma invariant. Okay, what does gamma invariant mean? Well, gamma is acting by homeomorphisms on K. It maps sets in K to sets in K. So when I precompose that with a gamma element, I don't change the measure. And this is actually going to be the key definition that we're going to be using today. Number 5, which is kind of a cool property, I think. So gamma is non-amenable if gamma does not admit a Ponzi scheme. Okay, everybody know what a Ponzi scheme is? It's when you like steal money from people. We'll talk about what that is. I'll give you a mathematical definition. And then 6 is gamma is not paradoxical, i.e. it does not admit a paradoxical decomposition. Okay, so subdefinitions. So this was a definition, but now I have to define the things that appear in the definition. So definition. And I'm not going to tell you things on everybody. Okay, so does everybody know what a measure is in general? Okay, so I'm not going to define this. The measurable sets are 2 to the gamma, so everybody's measurable. And what do I know about a measure in general? A measure in general, oh, I didn't say it was a probability measure. That's very important. Okay. Counting measure is a left invariant measure. So I hope you were already thinking this was either wrong or I'm going to be talking about all groups. Okay. So there is a left invariant finitely additive measure on 2 to the gamma. That is not a significant property unless I say probability or finite. Okay, probability means the total mass is 1. So I have a probability measure. Finitely additive just means I'm only allowed to take sums of finitely many disjoint sets. Normally measures are for countable unions of disjoint sets, et cetera, right? So it's just a finite version of the regular measure that you're thinking of. What is a Fulner sequence? So this one is for 2. There exists a sequence of Fulner sets. Well, there's different ways of describing the Fulner condition. They're all equivalent, and this is the one I'm going to use. So let's write it this way. Fn is a sequence of Fulner sets. Means that, well, they're nested. And they exhaust my group gamma. And they're sort of asymptotically invariant. So Fn gamma Fn divided by Fn is finite. Okay? So from this, let's think about what this definition means. Yes, thank you. Not just one special gamma. Thanks. So, yeah, so what is this? These Fulner sets are very strong. It's a very strong condition. And if you wanted to work with proving these equivalences, the sort of easiest ones are to start with the Fulner sets and kind of move implying the rest of them. Right, so these Fulner sets essentially allow you to average, yeah? Yes, I can. Thank you. Okay. So let me finish saying what I was going to say, and then, so basically they're allowing you to do like an average, but asymptotically. So if I have z, which we all know looks like a line, n, and I was giving a talk, and I put the cardinality of this was 2n. It's 2n plus 1. Okay, 0. So here, this is my Fn, okay? And then when I shift it, by the way, what does this symbol mean? So if I have A and B, the symmetric difference of A and B is that. So this is my set Fn. If I shift it by gamma, well, let me just shift it by 1. So it's going to be this set, gamma Fn, right? And if I'm looking at what is not in the intersection, Well, in this case, it is 2 elements. So let me maybe call this gamma 1 to correspond to the translation by 1, which I'm adding, I'm writing multiplicatively, right? This is 2. And then the cardinality of this set is 2n plus 1, not 2n. And then this goes to 0 as n goes to infinity. If I wanted a higher power of gamma 1, then I would just, take a larger set. Obviously, if I take gamma 1 to the power n, this is not going to be like a good estimate, right? So whatever gamma is, this is individually pointwise for gamma. I'll just take a bigger set, and I have this asymptotics. So because these are asymptotically invariant, they allow you to sort of asymptotically average. And this is exactly what is going to help you in a lot of those implications. Yes?
So are you taking the limit there when you have that
oh, yes, this is finite. Everybody was finite. That was silly of me. I don't know why I wrote that. N goes to infinity. Yes, thank you. This goes to 0, that one. Pierre. Okay, I make a lot of typos, so please correct me. Okay. Right, so that was that. I defined 2 almost invariant vectors, also very important. So for 3, we're going to need this definition. So this was a particular instance of what's called a unitary representation. So L2 here is a Hilbert space, right? So I'm going to define almost invariant vectors for a general isometric action. So H is a Hilbert space. Okay, e.g. L2 of gamma. And U of H is the unitary group. Okay, it's linear M from H to H, linear isometries. Okay, so that's maybe the warm-up. And then the definition. So I have pi, a unitary representation, okay? So an action on a Hilbert space by linear isometries. Linear means it preserves 0. Later, we're going to be looking at affine isometries. Is said to have almost invariant vectors, okay, if there exists a sequence of Vn in Hn such that I'm going to have a very similar property over here, that pi of gamma Vn minus Vn divided by Vn goes to 0 as n goes to infinity. And this is, again, for every gamma and gamma. Okay? So notice here, it's very similar looking, right? So this is a normalization. If I had taken, okay, so I'm, I think, writing in the forbidden zone, but maybe most people can see. Right? Can you see? So, I'm just saying that this is, don't forget this. Okay? So this is a normalization. If you're looking at unit vectors, obviously that won't appear. But many times people forget that. Okay? Right. So some people say, so what would be an example of such a vector? So given any representation, okay, if I don't put this here, what would be an example of a vector that satisfies this, no matter what representation I have? Well, I could take the 0 vector, right? It's linear, so the 0 vector is preserved. So that's one reason this is kind of here, but it's also making sure that you're not also approaching 0. Right? And what is HN? I don't know what HN is. Just H, okay? Don't forget. Oh yeah, so some people might say that they prefer that you almost have invariant vectors, okay? So another example of this, well, the 0 vector is invariant, but you might also have another vector that's fixed, right? Like maybe this is a trivial representation. Everybody's the identity, and everybody is fixing everybody, right? So that would be another case where this is just true on the nose, that it's actually equal to 0 rather than asymptotically equal to 0. So some people don't like the notion of having almost invariant vectors. They would prefer almost having invariant vectors, okay? But you see, there's an existence quantifier here, which means that you actually have something. So I prefer that you have almost invariant vectors, but it's two different ways of sort of looking at the same thing. Okay, what time is it?
So what is I sub gamma that you wrote there?
Oh, thank you. Thank you for the good question. I sub gamma, can I write it in this little box? I gamma is the trivial representation. Okay? So, so this curly thing is saying I almost have this as a subrepresentation. Okay? So if I wrote it, I'm not going to do that, I don't think. If I wrote it with a normal bigger or equal to, that would mean that actually this is an honest subrepresentation. There are vectors in my vector space that actually behave that way. So in this case, the trivial representation would just be, I have a vector, nothing happens to it when I apply any gamma. Thank you for the good question. Other questions? Clarifications? Okay. So that, I need to erase something. So that, okay, so Ponzi scheme. So this is named after somebody whose name was Ponzi, and this actually like really happened. I'm sure Wikipedia can give you some information. Okay, so P from gamma to gamma is a Ponzi scheme. So it's a map from gamma to gamma. Yeah?
I thought you were going to 4 first. The measure in 4 is a legit measure. It's sigma additive, right?
Oh, yes. Thank you. Absolutely. It's a real honest, it's also finitely additive, but it is definitely countably additive, which is called sigma additive. Thank you. Yeah, that's an important. Okay. So gamma is a Ponzi scheme. If well, it's a map from gamma to gamma. So I want to look at the inverse of any element in gamma. The cardinality of that, which is what I mean by the absolute value. If I want to be like extra redundant, I'll just put like a number sign there. This is at least 2. And what was the other condition? Yes, and it's a bounded distance from the identity, which means that there is an S in gamma finite such that P of gamma is in gamma S, okay? So this is what's called a Ponzi scheme. The idea is basically, it's another way to call it is a pyramid scheme. So basically, I try to get my friends to, everybody gives me $1. Now I have $2, and then I tell them to ask their friends, 2 friends for $1 each. Now they have $2, okay? And then, so if you do this process, you see that you get exponential growth. We heard about what growth was. So because there's only finitely many people in the world, and exponential grows very quickly, Ponzi schemes, you're not going to get away with it for very long, okay? Okay, so we're not really going to talk about that, but I like this characterization, and you don't often see it. And there's the clock there. Okay, so 6, definition. So what did I write? Gamma is not paradoxical. So this is, oh, by the way, so Ponzi scheme, being amenable is that you do not admit a Ponzi scheme, right? So, so this is also going to be a definition in the negative. So gamma is paradoxical if there exists an x, discrete countable, with gamma acting on x. This is my notation for action, okay? Is that okay for everybody? It's like a little mapping x to itself. And partitions x equal to A disjoint union B. And then A and B are themselves decompose into finitely many sets, possibly different number of sets. This is supposed to be a J. And G1 to Gn, H1 to Hm in gamma, such that when I translate by, okay, let me just write it down. So the disjoint union I equals 1 to n of GI AI is going to give me all of x, and also the disjoint union under the J's, let's say, Bj. Okay? So I have this countable discrete set. I decompose it into 2 pieces. Okay? Each of those pieces gets to be decomposed into finitely many. Maybe it's the same finite number, maybe it's not. And I can find corresponding group elements that are going to help me shift and then tile the whole space. Okay? So, so A and B are not empty, which follows from these conditions. And basically, yeah, so this is called a paradoxical decomposition. Okay, so if you play around with a free group or its a standard Cayley tree, you can see, hopefully, what a paradoxical decomposition is. And this is actually related to the Banach-Tarski paradox, which we're going to see on some day. Right? Maybe the person's not here. Okay, I think we're going to see it. Yeah, I think we're going to see it. If not, we'll make sure that we're going to see it. Please.
Definition 5, the set is it for all gamma.
This,
No,
5. Yeah, thank you. I keep forgetting that, right? Good. So you get 5 points if you pick, if you see that I forgot to say for all gamma. Yeah, thanks. Points for picking my my typos. Okay. So that was the definitions. And then here I have a list of a bunch of problems. I've kind of been saying them out loud. So those are going to be posted, I think, on the MSRI website, or if not, they're going to be sent out, or I don't know. You're going to get them somehow, okay? So from now, we're going to change gears, and we're going to look at linear groups, okay? So definition. Gamma is linear if there exists a homomorphism rho gamma injecting into GLN R. Okay? And now you're, yes? Yeah? You have a question? Now you're going to say, well, why'd you pick R and not C? Is that what you were thinking? No? Oh, you're like, stop talking to me. Okay. Okay, so GLN R, by the way, of course, so this is a parenthetical remark. So maybe I should do it in orange. Or maybe I should just, that's the end of the definition. Remark. So R embeds into C, right? Everybody know that? Okay. But also QP, QP also embeds into C, okay? And we're going to be talking about the p-adics later this week, very, very briefly. If you don't know what they are, don't worry. But if you almost know what they are, maybe you want to review. QP contains Q, and it has an algebraic closure called QP bar. And QP bar also embeds into C, okay? So if you want, you can talk about linearity. Oh, sorry, and then also C embeds into R2. Everybody know that? So, so this means that GLNC embeds into GL2NR, okay, by looking at the linear structure of C over R. But it also means that GLNQP bar embeds into GLNC, which then embeds into GLN2NR or whatever. So if you didn't like my choice of R here, it doesn't matter, okay? And actually, in this game, oftentimes changing your field is a powerful tool to do, and is an important technique. Okay, yeah?
So these embeddings you're saying like, is a field extension?
Right, okay, so this is an uncountable set. I could just like map it to an uncountable set. Indeed, these are field embeddings. Okay. Well, what do I mean by that? Well, what is a field? It has an additive structure. This is a ring embedding. Okay, it has an additive structure, has a multiplicative structure. Therefore, it is a field embedding. Sorry, I was not prepared for your question. It's a field embedding.
Fields are either embeddings or trivial anyways.
Right, sure. So I have additive structure. I have a multiplicative structure. So there's natural things you can do. Well, 1 should go to 1 because, you know, functoriality. But then from there, you automatically get Z goes to Z. And then from there, you get that Q goes to Q. And then from there, you get that Q bar goes to Q bar. So now you're out of choices, or you're out of, not choices, you're out of things that are imposed to you, okay? But now you have transcendental extensions, and you get to kind of pick those. Yeah?
I mean, the Z goes to Z is really, the embedding is the identity on Z and also on Q. But on Q bar,
yes.
Q bar goes to Q bar, it's not the identity on
Right, okay, so good point. So here I have absolutely, well, I guess I could take Z to minus Z. Could I? No. No, because of the square. Okay, so I can take Z to Z here is the identity. Q to Q, also the identity. But then when you're looking at Q, say adjoining square root of 2, okay, and I'm embedding this into C, or equivalently Q bar, automatically now I don't know how to do that right away. So I have two choices. And then more generally, when I'm embedding Q bar to C, I have Galois Q bar over Q, many choices of how to do that. Is that what you wanted me to say?
Yeah,
Yeah.
I just wanted to emphasize this.
That is choices, yeah.
Being the identity and stabilizing.
Right. And then, yeah, so this is very interesting, but let's not get trapped in there. Okay, so gamma is linear, means for me this, but if you don't like R, you prefer C or whatever, you can change your point of view accordingly. So we've been talking about linear groups. No, we've been talking about amenable groups. And so now the question would be, so a question would be, which linear groups are amenable? Okay? Right. So now I've been talking about discrete countable groups, and I'm going to suddenly switch to locally compact groups. So the locally compact linear groups that are amenable are essentially, well, what can I do? For some reason, I always look at determinant 1, but ON, okay? I'm saying that because in my notes I wrote SON, and I'll probably do it again, SON versus ON. So this is the orthogonal group. The orthogonal group is compact. Those are amenable, okay? Solvable groups which are essentially conjugate into the upper triangular group. Okay, so this is my floppy matrix notation. I have whatever I want on the diagonal, whatever I want above the diagonal, and 0 below the diagonal. These are upper triangular. This is amenable. Okay, yes?
What did you write below that?
Something you can't read. Conjugate into, okay?
Okay, so does that mean that like presupposing with some conjugation gives you?
Yes, precomposing with conjugation, which means I take a matrix and my group G, and so I multiply M, G, M inverse, and that's going to land me in there. So left multiplication by M, right multiplication by M inverse, or, okay? Thank you. Right, and then what can I do? Well, this is part of your exercise. You can take products, okay? So if I take ON times a solvable group, or I could even take semi-direct products, and kind of have one more group to tell you. I won't tell you. Okay, so I can, putting these together, which I won't do on this board. So using this and your homework. Another example that is going to essentially be the example is going to look like okay, so this is almost like a number triangular group, except that each diagonal entry I've sort of blown up to be a square matrix. And then maybe in here, I am allowing myself to have OK1. And maybe in here, I might have some diagonal matrices. Okay, abelian groups are amenable. Oh, did I give you? I didn't give you the examples. They were in the homework. So abelian groups, finite groups, compact groups, solvable groups, all of these are amenable. And so here, when I put these on the diagonal, if I had zeros everywhere else, that would correspond to a direct product. And then here, let's put, I don't know, OKL. So I can have this decomposition into upper block triangular, or block upper triangular, let's say. Okay, and since I said upper block triangular, I'm going to put stars here. Okay, so I can have whatever I want there, and this will be an amenable group. Right. Okay, so these groups are going to somewhat come into play for the rest of the talk, when we're going to be trying to understand which linear groups are amenable. So remember, I said one of the key characterizations of amenability we were going to use was the existence of an invariant measure. Okay? So now I'm going to pick a canonical or natural space associated to GL and R, and I'm going to say which groups have an invariant measure and kind of try to study that. And that's going to lead us into the rest of the week also. Okay, so which linear groups are amenable? I'm going to rephrase that question. Do you have a question?
Just what are K1 through KL?
Oh, integers.
Oh.
Okay, so did I change my notation? I did. Okay, so ON, this is the orthogonal group of Rn. And then I guess when I wrote that notation, I was writing it this way. And then I guess a restriction here, if this is in GLN R, would be that the sum of the Ki is n. Okay? Yeah. Okay, so I'm going to rephrase that question into which linear groups preserve a measure on projective space. Okay, so projective space. You may have seen this before, and if you have seen it before, it's possible you've seen many, many different notations for projective space. I'm going to be sometimes projectivizing vector spaces. So projective space. So oftentimes people will say RP2 for what I'm calling PR3. Okay? So we write RP2 because it's over the reals and it's a two-dimensional object. But here I've started with a three-dimensional object and I've projectivized it. I'm assuming you're going to know that, I'm going to tell you the definition in a second. I'm assuming that you're going to know that it has become two-dimensional. And actually, for me, the fact that it has become two-dimensional is kind of irrelevant. Okay? So I really want to remember which vector space I'm kind of coming from. Right, so what is this object? So PRN are equivalence classes of lines through the origin period. Okay? And it has a topology, which is a natural topology. I'm going to just draw some pictures, and then you're supposed to kind of infer from that what the topology is. Again, that's not really going to come very precisely into the picture. So what's RP1? Okay. So I have a line. How many lines through the origin do I have? 1. So this is a point. And if I ever have a point, I'm going to call it star, because it's just like the one star in its universe. Okay? Now, let's get a little fancier. R2. Okay? So I have R2. Here's my plane R2. The origin, it doesn't count because I'm looking at equivalence classes of lines to the origin, which means if my equivalence classes are going to be disjoint, I'm going to be considering the points as belonging to the same line, except for the origin. Okay? Well, the first thing I see is that I can find a representative of every line that lies on the unit circle. Well, actually, I'm going to find 2 representatives. I'm going to have the sort of positive one, let's say, in this picture, the positive quadrant and the negative quadrant, okay? And so I can sort of contract R2 to belong to the whole circle. So what I have found is that for every line through the origin, let's actually draw the line. Okay? For every line through the origin, I have found a smaller collection of representatives corresponding to the points on the circle. And each line through the origin has 2 such points. Okay? So now what do I need to do? I need to take the equivalence relation corresponding to being diagonal, being antipodal across the circle. And so what I'm going to get is a circle again, okay? It's actually a double cover of the circle. And if you are looking in the complex plane, which I earlier said was the same as R2, then this map would be z goes to z squared. Okay, so it's like a double cover. Right. So now, okay, R2, this is, everybody knew what that was? S1, sorry. Okay, S1, circle. So far it's not looking that interesting. But when you get to RP2, or P of R3, it starts to get more interesting. And I'm going to leave this to you as an exercise. But it's equivalent to this filled-in disk. I'm going to glue things along the boundary. I'm going to glue this point to this point. And I'm actually, the gluing that I did here was exactly, was exactly this antipodal thing, right? So it's like you're chasing a dog or something around a tree, and you're never going to catch each other, right? So that's exactly what's happening along the circle. In fact, this circle is exactly this circle. But what happens to the interior of the disk is more complicated. So if you haven't seen this before, play around with it. Maybe I will just briefly say that if you punch, so everybody wrote this down, right? So if I take the projective plane, okay, this is that. And I'm going to remove a disk. So I started with that, and I punched a hole out of it. This is a Mobius band. So if you don't know this, play around with it. It's fun. Yeah, so those are some projective spaces. Okay, some facts. So the real projective space is a compact metric space. When I was talking about acting by homeomorphisms, I was saying on a compact metrizable space. I'm calling it now a compact metric space because I'm actually going to use a metric on it. It doesn't matter which one, as long as it gives you the same topology. And these were equivalence classes of lines in Rn, and they are sort of cousins or sisters with another interesting compact metrizable space called the Grassmannian. Okay, so this k is an integer. And this is in the same way that PRN were equivalence classes of lines to the origin. This is equivalence classes of k-dimensional subspaces through the origin. A subspace goes through the origin. Subspaces. So in particular, when k equals 1, we have that the Grassmannian 1 Rn, I switched ends, is P Rn, and I did not write the name. This is Grassmannian. I may have put too many ends in there, I'm not sure. Variety. Okay, so another fact about them is that they are also compact metric spaces or compact metrizable spaces. So also compact. Okay, so I hope you can see that these are very natural compact metrizable spaces associated to these linear groups. So it's a pretty natural question to ask, you know, if I have an invariant measure on, we're not going to look at the invariant measure on the Grassmannians, but you can sort of generalize what we're going to do to that. Which groups have an invariant measure on the projective space, okay? Or rather, what do I know about them if I have an invariant measure? Okay, questions? Yeah?
Is the answer to that question related to immutability?
Right, good question. Yeah, that's a good question. Can I paraphrase your question? Yeah. So I asked this question, and now your question is, what are you talking about? I'm lost, or I'm not saying you're lost, but somebody's lost. Okay, so what does this have to do? So I gave you 20 million definitions for immutability. Let me recall the relevant one. So gamma is immutable if for any now I can actually, let me rephrase it for G, because I can. Okay, so G is immutable, which actually I'm also shortening to Mn. If G, whenever I have a continuous, strongly continuous, just think continuous, action by homeomorphisms on a compact metrizable space, then civil space, then there is a mu in the probability measures on K. These are honest to goodness, sigma additive probability measures on K. That is gamma invariant. So gamma star mu of some set E is mu of E is defined to be gamma inverse of E. Sorry, gamma inverse applied to E. That's just the definition of the push forward measure under mu, of mu under gamma. And invariance means that this is just back to where I started, okay? So I gave many equivalent definitions, and this is the one that I'm trying to understand right now for two reasons. It's going to lead me to what I'm doing the rest of the week, but it's also allowing me to think about if I have an amenable subgroup act in GLNR, and that means it has an invariant measure here, can I understand something about that group, okay? And there's a question. Yeah, so I was like, don't ask me that. Okay, so, no, it's okay, I'm kidding. So it means that I put the product topology on G cross K, and the orbit map GK goes to GK is continuous. It's continuous. Okay, other questions? Okay, so did I answer your question? Yeah, okay, so I defined amenability, and now I'm trying to understand if I'm an amenable subgroup of GLNR, can I say something, okay? And we will be able to say something in stages. I'm not sure how much we will in the next 15 minutes or 12 minutes. Okay. So I was there, I was here. I'm going to actually write down a lemma that I'm going to then prove. And this is my next board, but maybe it's a weird board to write it on. So I'm going to write it on this one and then go back to the proof over there. Okay.
Is that a for all gamma containing gamma?
You know what? When I was writing this down, I was like, don't forget the gamma. And then I forgot the gamma. Thank you. 5 points. And now if you were my students in calculus, you'd be like, what do we get for the points? I'd be like, nothing. My heartfelt thanks. Okay. Furstenberg lemma. Okay, so mu is a probability measure on real projective space of dimension n, and gamma is just any subgroup. Okay, so if mu is gamma invariant, okay, what does that mean? It means that the push forward under every little gamma in capital gamma of mu is again mu. So if mu is gamma invariant, then either gamma is precompact, i.e. its closure is compact, or there exists a non-trivial subspace. Okay, so non-trivial means it's non-zero, but it's also not everybody. Such that mu of v is positive. Okay, and you know what? It's going to be called v0 in the end, so let me go ahead and call it v0 now. And it'll match what I'm about to say too. And there exists a gamma 0 in gamma of finite index, stabilizing V0.
So,
Mm-hmm. Who said so? Yes? Uh-huh.
The V0 with brackets means the projective space of V0 inside P over R.
Yes. Thank you. So okay, can I elaborate on what you just said before you ask whatever you were about to say? So what do I mean by this? Okay, so V0 is a subspace. Let me actually, let's write it in this board I didn't use. Let me finish with this and then, can I erase this? It was your, yeah. Okay, hold that thought. Right, so remember when I was drawing this picture, I said that that this was PR3 and that PR2 was a circle, right? And another way to see that circle was also to write it this way. So I have an inclusion of this circle into this boundary as it's written, as it's drawn here. It's not actually a boundary. And more generally, if I have V a subspace, and that's exactly why I was using this, well, one reason why I was using this projective notation. Any subspace has its own projective space, right? This is a linear subspace of some dimension less than n, okay? And let's assume it's not 0, although if it was 0, it would just be the empty set, so the empty set is also a projective space. So P of V then naturally includes into P of Rn. And in what I wrote there, I just called this square bracket V, okay? Yeah, another notation could be like V bar, the equivalent, all the equivalence classes of all the things in V, okay? Were you going to add something more to my statement? And you had a question.
I didn't remember what E was over there.
Oh, yeah. So E is a measurable, let's say E is a Borel measurable set. This. Okay. Other questions, clarifications?
Here is for all actions on the cleric system.
Yeah, thank you for all. That's a very, yeah, okay. So why for all is important here? Well, give me your favorite compact metric space and your favorite group. I can make it do nothing, okay? Doing nothing is always counts, and then any measure will be invariant, okay? So every such action. Good question. All good questions. More questions. Because, okay. So let's see how much of this proof we can do in 5 minutes. So proof. So what did I say? Either gamma is precompact or something happens. So assume gamma is not precompact. Okay, what does it mean to not be precompact in the ambient group? Okay, it means there exists a sequence of elements going to infinity in G, L, N, R. Okay, now you see why I've been using capital N. So I'm going to look at sequences. So I can find a sequence of elements going to infinity. What does that mean? It escapes compact sets. Okay, so actually, I'm going to slightly edit what I have here just because I only have 5 minutes. And okay, I'm going to put a P here. Okay, everything I was going to say was going to work anyway, but it'll be a little bit simpler. P. Okay, P means projective, means GL and R mod the center of itself, which is center is diagonal matrices. Diagonal identically lambda. Okay? Okay. So, right. So I have these going to infinity in PGLNR. So what does that mean? It means that it's escaping compact sets. Okay, but, and not but, because it's not precompact. So now I'm going to choose lifts of gamma n in GLNR. Okay, so I'm going from this quotient group, GLNR modded center, back up to GLNR. I'm going to call them gamma n tilde, such that the norm, I'm going to tell you what that is, the norm, which is the maximum of the absolute values of the ij entries in this matrix, okay, is going to be equal to 1. Okay, so I have this matrix, projective matrix in PGLNR. I'm going to find a lift that has this norm equal to 1. Okay? And now why do I want to do that? Because, and this is in the n by n matrices. Okay? N by n matrices, I have a norm. The unit ball is compact. So this is going to allow me to extract a convergent subsequence. Okay, so so now it follows that there exists a subsequence of gamma n tilde, which I'm going to call gamma n tilde again, that converges to G in the matrices M and R. Okay? So I have like 1 minute. I'm just going to make sure that this point is super clear. So I'm lifting. So I have norm 1. Okay? That's a compact set. I can find something that is converging to something. Now, why do I know that G is not in GLNR? Well, this was going to infinity here. So it's also going to infinity in the lift. Okay? But going to infinity doesn't mean my norm is going to infinity. It just means I'm leaving the GLN group. What does it mean to be in GLN? It means I'm invertible. If I fail to be invertible, it means I have a kernel. So this is because the gamma n, we're going to infinity in PGLN R. And so the conclusion is that the kernel of G is not 0. Whoops. Right? But I also know that its norm is equal to 1. So its kernel is not everybody either. But the norm of G equals 1. So the image of G is not 0. Okay? I think this is a pretty cool step. Everybody understand this? Okay, so I have two subspaces now. Okay, and we're going to then show that the measure of the measure of the image of G union V is equal to 1, where V is a limit of gamma and kernel of G, limit point in the Grassmann variety. Okay, so I'm out of time, but from here on, it's just sort of calculating stuff, okay? The really, really clever idea is playing this game of swapping out your lift so that you can sort of go to infinity and not go to infinity at the same time. That gives you a non-trivial kernel and a non-trivial image. And that gives you these two subspaces. We'll then show that this has measure 1. And then to finish the lemma, we will find a minimal dimensional subspace that has positive measure. That will be this one. And then by minimality of the dimension, you will get that this is finite index. So I'll finish that in the 5 minutes tomorrow. So thank you.